language models and physics. So let's give her a warm welcome and take it away.
Hi, everyone. It's a total honor and pleasure to be here. I don't know if you have heard, but a lot of folks lately in our field and in the industry broadly are pretty interested in language models, and especially LLMs. I would even argue it's maybe reached peak like the hype cycle. So there's a lot of excitement and potentially hype about language models. But there's another piece of the story that we've heard some mentions about today that I want to focus in on, which is that for all of their amazing capacities, language models also have a bit of a problem, which is that they struggle with mathematics and with some pretty basic arithmetic tasks like addition and multiplication of large numbers. So it's kind of interesting, but maybe not so surprising of a result, given that these are statistical machines, that they struggle with precision in some of these very clear tasks like arithmetic. So let's look at a quick example. This is me asking ChatGPT to multiply two 4-digit numbers. And if I ask it to really do this in a zero-shot context, to just give me the answer, no reasoning, it gives me a number that looks, at least to my eyes, like the rough order of magnitude correct answer. And maybe if I wasn't careful, I would just take this on principle to be correct. But if I actually checked it with my calculator, I'd see that it's actually wrong. It got pretty close, but it messed up some of these digits in the middle. And what we would find if we repeated this experiment multiple times, even with GPT-4 latest and greatest, we would find that it would fail over 95% of the time on this particular task of multiplying 4-digit numbers. So this is kind of surprising to a lot of folks who look to GPT-4 as a tool that can solve almost any problem very easily. And I think it really speaks to this question of how language models represent numbers and how they've really struggled in how to distinguish representations of numbers from any other kind of text that it might see in its corpus. And sort of a core problem of this, right, is that the way that language models are trained is on a finite vocabulary. And that vocabulary is kind of like a bag of Scrabble tiles, where you can mix and match those Scrabble tiles to arbitrarily represent any word. So maybe your Scrabble tiles are characters, or maybe they are subwords, or maybe they're words, but however you want to break it down, you ultimately have to transform this problem of representing any word into a finite series of tokens. This is obviously an issue when we're talking about representing numbers, because numbers are not finite. So we can dig into this a little deeper. We can look at existing word embeddings and see if they're able, say we do train them to represent numbers within a certain domain. So in this case, these are some folks who trained various word representations to represent numbers between magnitudes of -500 and +500. But you can see in all these red values are when they ask these models to extend out of distribution, outside of the training task, and none of these embeddings are able to accurately extend out of distribution on even just the magnitude of the number. And we also see this in the language model's confidence about a number. So we might expect that if language models have kind of a good internal representation for what numbers are, if you ask it to predict, for instance, how much does an egg weigh, you might expect something like a Gaussian distribution roughly around the correct answer. But that's not at all what we see. We see these huge spikes in terms of its confidence. And then once you go way higher than the answer, you might see a huge spike in confidence. So this is not at all what we would want an internal representation to look like for a model that really has a good handle on what numbers are. We can use a couple of clever tricks that researchers have found over recent years in how we represent numbers in words to make this performance a little better. So this is an example of a couple of tricks for just different ways of writing out the number to the language model to make it understand it a little better. And this is on the task of multi-digit addition. And so I just want to point out these red and black lines here, where depending on what representation you choose, you might be able to extend your performance to larger and larger numbers. But at the end of the day, we are not seeing a saturation of 100% accuracy, which is what you might expect if the model is actually learning the rule of addition. And instead, we are just sort of extending the failure rate for some of these methods. So we can kind of generalize this and think about what's the sort of scope of numerical embeddings. And this kind of it ranges all the way from tokenizing individual digits. So this is sort of the sparsest vocabulary or the sparsest Scrabble tile bag that you could imagine. You just have tiles representing each of these digits, and then you combine those separately. Or you can scale all the way up to tokenizing every single number. So imagine a Scrabble bag where you have new tiles for every new number that you want to represent. So depending on your preferences, maybe you want to choose something in this range. But clearly, all of these are going to struggle with representing some new number that you can propose to this system, and it's not going to scale well. Your size of your vocabulary is going to skyrocket. Okay, I want to pause. Why would scientists care about this problem? We are not seeking additional tools to solve the problem of addition and multiplication. Obviously, we have calculators in Python to help us with those tasks. And it's not like anyone is using ChatGPT to copy and paste their data directly into the tool and ask it to analyze it. Unfortunately, this is not totally correct. In recent years, this is in October of last year, we started to see some new results come out from some folks who are literally directly putting their data into pre-trained language models like ChatGPT and asking it to make time series predictions. And what they found is that even with this really simple technique, GPT's predictions, which are in purple, line up really nicely with even neural network baselines. This is a temporal convolutional network in green, or just a simple moving average baseline in orange. So it turns out that they were able to sort of see some surprising results with even this very rudimentary setup that you would not necessarily expect to work all that well. And we've seen extensions of this, some sort of studies about how to contextualize this problem. Maybe you can include more information in the prompt to the model about how you want it to model, and that can improve performance a little bit too. So this is with GPT-4 compared with a time series prediction. And these researchers look through a bunch of baseline time series data sets and are able to get pretty strong time series predictions in this case. So in that, we are starting to kind of see that in certain contexts, language model architectures are actually able to model numerical data relatively well. You could say that maybe this is more about how difficult it is to predict long-term time series predictions than about anything inherent about that language model structure. But nevertheless, it's surprising, and it's interesting that folks are moving in this direction. I would also posit that maybe we've been evaluating language models on the wrong kinds of numerical tasks. They are statistical in nature. And so maybe we never should have expected them to perform well, for instance, on precise arithmetic tasks, but maybe they were always better designed to perform well on messy, real data scenarios. But okay, but even still, why would anyone want to endorse this as a valid method of scientific inquiry, right? It seems like we're going down a slippery slope if we sort of extend this further. So what I want to argue is that language models are very flexible. They are naturally able to combine different data sets that are represented in a number of different ways. And I think that this is going to be essential as we start to build scientific foundation models that can have arbitrary formats for their data. And we capture data from lots of different modalities. And so we need some kind of input structure that is deeply flexible. This is a big reason why we don't have a science GPT nowadays, right? Is that it's relatively easy maybe to think about how do we combine multiple input data sets that nicely fit together. So we can combine Shakespeare and we can combine Reddit data because those are both language formats, and we can just concatenate them all together in the inputs. And similarly with image data sets, we can also imagine how do we combine many images together. But science data and physics data especially is kind of different. It's very diverse in how we represent our data. And so it's not at all clear how we would take data from the Large Hadron Collider with data from JWST or data from LIGO and combine all of these meaningfully into a single science GPT. And that's why this doesn't exist yet. And we've really only seen it within specific subdomains that share modalities and representations. Moreover, I think this is important too, scientific data really requires context. You can imagine a lot of images where you don't really need to provide context to the model, but scientific data is not one of those domains. These are two images, but to the model, it has to understand how these images were captured and what these pixels actually represent in order for the model to make meaningful predictions about these two images. So we, in our task to maybe think about building a foundation model for science, like a science GPT, we ultimately need to search for an embedding that is able to combine all of our inputs into a single embedding space. So it's about finding some sort of common language that our model will be able to understand. And one quick caveat that I want to make on this is that I think that the ultimate vision for how I can imagine building something like a science GPT is using language as a baseline, but that doesn't have to be to the detriment of taking advantage of more efficient representations for certain types of modalities that we already know very well. So you can imagine, for instance, when you're texting someone and you say sounds good, and then your iPhone knows to replace sounds good with an emoji. Similarly, you can imagine having language as kind of your baseline glue as how to represent all of your data, but selectively, we can have more efficient representations of certain types of data that we are already very familiar with. So a couple of examples of what this might look like in practice for science. For instance, going back to Paul Nee from 2023, this could, you can imagine taking, for instance, images, feeding those images through a vision transformer, and then that creates a highly efficient embedding for those images. Or in this case, they also were dealing with robotic instructions. And so maybe they have a clear way of representing robotic instructions, but the rest of the prompt can be given with arbitrary language. Relatedly, this is from Apple from the past few months, thinking about in the space of images, you know, there's many ways to represent images, and it doesn't have to be just through RGB tokens. It can also be a segmentation map or a depth map or flip features. And so these researchers thought of ways to embed certain types of images in very specific ways in order to build a more general representation. And we are starting to see this also for specific physics objects. So for instance, like jets, where we might want to design some sort of specialized, efficient representation of particle jets inside a general model of physics. And so maybe we can replace those selectively within our inputs. Okay, but given that for today, I just want to imagine we do the simplest thing possible, and we use a text representation of our data, such as copying and pasting our data into ChatGPT. How's a way that we can sort of improve this baseline structure, because we know that we can. I think it's clear that we can do better than discrete tokenization for numbers. We know this, numbers are continuous, and especially in science, this continuity is going to be an important property. So let's imagine using just one token to represent any number in a contiguous way. You can almost imagine this as adding just one token to your Scrabble bag to represent any number, and we'll treat that specially for numbers. So this is what I and some of my colleagues have released towards the end of last year. It's this method called XFAL. It's a continuous tokenization strategy for numbers inside of language models. And we do this specifically for scientific applications. So I'll quickly just demonstrate how this works. So say we have a language representation that has a number embedded in it. The first thing that we want to do is convert this into text and then extract any numerical values. Then we want to tokenize. So to tokenize, we sort of pull up our tokenizer dictionary. We can see what tokens correspond to each of our inputs. And we have a special token corresponding to the number token. So given that dictionary, we'll replace all of our actual words with tokens representing those words for the number token. But then we don't forget about the value of the number. And then we actually multiply each of these numerical embeddings by the number that it represents. So we have an element-wise multiplication inside the vector representing that number, and we scale it by the magnitude of that number. Then on the inference side, we can have a new token that represents a mask, where basically you cover up part of the sequence and you ask the model to predict what's underneath that mask. And so maybe we have a new sentence, like new on mask. We want the model to predict what's underneath that question mark token, that mask token. So again, we go through the same process. We pull up our tokenizer dictionary, we tokenize, and we look for a token corresponding to the mask. And then if the numerical token is predicted, then the model has a dedicated transformer head or oriented around predicting the value of that number. And so if underneath that mask, if it ends up predicting a numerical token, then a dedicated head will be prompted to ask what is the actual magnitude of that number? And then that magnitude is fed in at the end of the inference process. So I just want to also comment that in practice, we really are dedicating this to training on highly dense numerical data sets. So we're not necessarily trying to solve a problem of how do we represent numbers in language corpuses, but we're really thinking about the corpus being a numerical data set at the end of the day. Okay, so this overall encoding strategy has 3 basic benefits. The first is continuity. So language models are discontinuous in their sort of default form when you think of them as number inference machines. And so this strategy allows the language model to become continuous end to end with respect to that number. And we posit that this makes it much more appropriate for a lot of scientific contexts. Next is interpolation. So in part due to that continuous property, it is able to get better out of distribution predictions than many other numerical encodings. And then finally, efficiency. This is a consequence of just using one token to represent any number, is that we don't have that scaling issue that I mentioned earlier. So it requires less compute and less training time to achieve pretty strong results. So I'll show some quick results. This is XVAL tested on the task of temperature forecasting. And this is a real world data set, the AR5 data set, predicting next step temperature in many different locations on Earth. And we find that XVAL achieves the lowest loss in by far the shortest amount of time, just about 9 hours compared to some of these other baseline methods that took much longer. And we also see that XVAL's predictions are much more stable. They don't suffer from these kind of outlier effects that are due to uneven distributions of these numerical tokens in the baseline categories. When we also test XVAL on the task of training on simulated planetary orbits, we also see that it shows really nice out of distribution predictions. So this plot is showing an interpolation out of distribution. So the model has only seen, this is the semi-major axis of the first planet in orbit. The model has only seen either less than 1 or greater than 1.16. So everywhere in this region was not seen in the training data set. And if we ask all these baseline methods to kind of interpolate and guess what the true semi-major axis should have been for those samples, the other baseline methods are not able to kind of continuously interpolate between those points, but XVAL is the one that gets by far the closest. And we see this also with inferring the frame rate of the simulation. So this is delta T of the simulation. And the way that we designed our experiments is that we only selected a handful of discrete values that could possibly emerge in the training data set. And those discrete values are shown in the gray lines here. And then we ask XVAL to interpolate between those points, and it's able to really nicely extend between just those discrete scene values. And then this I also find really cool. We also tried masking multiple time steps all at once for XVAL, and it's able to predict all 10 time steps at once, for instance, for all of the different planets in our orbit. So, so in this case, all of these different time steps, again, the prediction is not autoregressive in nature, but nevertheless, if we mask all of these time steps, it's able to nicely follow each of the trajectories of the planets in all of these test simulations. So, I want to emphasize that we should certainly not expect LLMs to be perfect calculators, but maybe I'm arguing that by testing whether they can be calculators, we've missed this kind of maybe larger potential area of application that is numerical in nature for language models. And I think that modifications such as XVAL can help us take sort of the core structure of language models and make them more adaptable and more suitable for scientific applications. And I think someone mentioned this earlier today too. I also just wanted to quickly highlight that language model LLMs in general have been seen as kind of black boxes, but we are only lately kind of scratching the surface of interpretability for these tools. And I think building up our interpretability of language models will also help adapt them to be more suitable for scientific analysis. So this is a diagram from Anthropic from last year, thinking about patterns of neurons in their activations. And they're able to find cohesive and predictable patterns of neurons and what they activate on, even in something as large and complex as Claude as a large language model. And then this is also a recent result from my colleagues and I, thinking about, can we really nail down what is every layer or each part of the transformer actually doing in a certain calculation. So here we're testing whether a transformer can count. And that task looks like this, where your input has a bunch of zeros and ones, and then we create little boundaries. So we create regions with square brackets in that input, and we ask the model to count how many ones are within each of the sets of brackets. And so ideally, we would want it to be able to count, oh, there's no ones here, but there's 2 ones in this region. And we find that we can really predictably explain each of the parts of this model and what that model is doing overall with a relatively simple formula. And when you overlay that formula's predictions with what the transformer is actually doing, they line up really beautifully. So these are small bits crawling our way towards interpretability for large language models. But I think these are the types of modifications that we would need in order to make this more viable. Okay, and then last, I just want to kind of comment, this is a little more philosophical about how I hope that we are building foundation models in science. And specifically, I want to make sure that if we are building these tools, that we're doing it in a principled way, in a way that reflects our highest priorities as scientists, as opposed to something that's happening to us that we have to adjust to. So, I want to be proactive about how we're building these tools. And the art world, for instance, is one of these worlds that's already grappling with these questions. And I know this because I am an artist working with AI, and many of my colleagues are dealing with this too. And so I would just encourage you all to pay attention to how are, for instance, artists dealing with the introduction of foundation models in this space. It's not only about who owns the data or who owns the generated output, but it's also about how do these tools change what it feels like to be an artist, and does it sort of take the joy out of the process? And I don't think our field is so far away from some of these discussions. When we first sort of saw the onset of ChatGPT, there were a number of studies done about sort of our exposure to large language models in general, and they found that scientists and researchers are actually among the top of the jobs that are highest in exposure for these tools. So I wouldn't want us to get complacent and think that the job of a scientist is not going to be affected by these tools. And so I'm excited to create them, but I also think we need to be careful about how we shape them. So I just really want to emphasize that we have this precious opportunity to develop these tools that are aligned with our scientific goals of promoting understanding, curiosity, and discovery, and that nobody else is really going to do this for us. So as we are building these tools, are we making these tools just to make science more efficient? What do we mean by efficient? Is that something that's going to make our lives better or worse? Will it make doing science better or worse? And are we building tools that are going to make us feel more curious about our work, think differently, and want to take risks? So for me, when I want to think about building foundation models for science, I think about efficiency, not in terms of how quickly can we crank out more papers, but rather about efficiency from training, from a training perspective. So say that I'm dealing with a regime where there's a very expensive simulation or not a lot of data. can these foundation models form a stronger baseline for training neural networks on this type of data? Or similarly about interdisciplinarity, how are these foundation models able to give us a wider vantage point beyond our individual subdisciplines and potentially point out relationships or patterns among methods or data from these different subdisciplines? And finally, creativity, I think. It's something we all aspire to build tools that help us tap into our creativity as scientists. And so that also means reflecting on whether these tools are making us feel more creative or not. But ideally, they will be able to bring out very inventive strategies or new ways of thinking about our data. Regardless of how we decide to move forward with building foundation models for physics, whether language plays a big role or not, I think we will find that physics as a field will benefit from kind of remembering the value of language. I think this is something that we've kind of, it's been historically de-emphasized maybe in how we've thought about technology in the field of physics. But language is a really powerful tool. It allows us to process very complex information, and it connects code and mathematics and intuition. And it's ultimately what makes physics discoveries meaningful. So I hope that, however we move forward in this field, that we find ways of bringing context and language into our data, because it's a key way of representing our information. Okay, and then lastly, I just want to conclude with this quote. This is from a New Yorker article reflecting on kind of the end of coders from someone who is a professional coder and is also dealing with ChatGPT. And I think it really captures for me the way that I would aspire to build foundation models for physics. In chess, which for decades now has been dominated by AI, a player's only hope is pairing up with a bot. After machines conquered that game some 30 years ago, the fear was that there would be no reason to play it anymore. Yet chess has never been more popular. AI has enlivened the game. Meanwhile, at the highest levels, grandmasters study moves the computer proposes as if reading tablets from the gods. Learning chess has never been easier. Studying its deepest secrets has never been more exciting. Thanks.
Thank you, Mariel. We have time for a bunch of questions. Let's start back over there.
Thank you for a very nice talk. So you've introduced the problem of trying to represent numerical data together with text, and I think the approach you have presented to us has to do with creating the proper tokenization strategy so that we can embed numerical information. There are, of course, other alternatives. For example, trying to align embeddings from purely numerical data objects with the embeddings of text through, for example, some contrastive learning approach. Do you have anything to say regarding that alternative way to do this alignment, and whether it would be preferred over this purely textual embedding and tokenization things?
I think it's a great question. I don't have any specific backup slides on the idea of contrastive learning, but I think it's an excellent idea. A lot of the baselines that we thought about were kind of from the NLP history, thinking about how NLP researchers have probed numeracy in large language models in particular. So it's true that I think maybe the way that I've thought about this problem has been informed by how NLP folks are interested in mathematics and thinking about what they succeed at and also what they miss in some of these methods. But contrastive learning could be one of these tools that we as scientists can help bring to the conversation to think of even more inventive embeddings for new numbers, for instance.
Okay. Sorry, going back to your intro, did you ask XVal for a random number? Did you get uniform distribution? And also, humans also give very spiky distributions for random numbers, like 7, 37 prime numbers. does this mean humans also don't understand arithmetic in general?
Yeah, it's a good question. Yeah, because it's been pointed out that language models have a preference for generating the digit 7 more than the other digits, right? And that's kind of reflecting the fact that humans have an intrinsic preference for the number 7. So yeah, it definitely should encourage caution when dealing with these language models and thinking that they can really provide truly random answers. For Excel, I can't think of a test that approaches what you're describing. But we tested on various predictions and then interpolation out of distribution. But I think it's a good question. So it's not to say that XVAL is not as, of course it has its limitations. Yeah.
Yeah, so the problem with the arithmetic in these large language models was a big problem, I think, in GPT 3.5, and then before it was a lot better. And now what they do is it just runs some sandbox code to do the arithmetic. And it seems that, you know, if you want like multiplying large numbers, obviously, you know, you might be able to learn it, but if you're doing a much more complicated, take a square root of a very long number, you know, why wouldn't you want to just do it in sandbox? So what's the advantage of using this tokenization scheme as opposed to just saying, you're asking me to do an arithmetic problem, let me just run it on a calculator, which is what we would do.
Exactly, yeah. When I first started this work, I was thinking that it actually might help with multiplication or arithmetic in general. We found that when we tested this on arithmetic examples, it was not state of the art. So it sort of taught me to think about, okay, where is the region of applicability where it could really excel? And so I think the 2 points I want to emphasize for where this matters, other than using these built-in tools, would be for these cases where researchers are using LLMs directly on time series data predictions or predictions in general on scientific data sets. And then in general, as we think about combining modalities in a scientific foundation model, where language can form the baseline of our representation for different data inputs.
So you're saying that even if you augment XVAL with the ability to access the calculator, it's still useful in these tasks?
Right, I think it's useful in cases where you don't know the right formula to plug in, where you want it to predict complex time series dynamics. And maybe you don't have the right equation to run through your simulation for. So I think if you have a messy real life data set where you don't necessarily know the fundamental simulation or the right answer, Excel could be a better bet.
So I have two questions. The first one, how much is like on the normal transformer or GPT is predicting time series just a memorization game? Like it could be regurgitating something that might have seen in training data and like maybe sines and cosines or like these beat kind of signals were in the training data and they were just like perfectly constructed. Is that something you might have tested or seen?
Yeah, so in time series in general, I think a lot of the baselines that I showed in previous results, basically none of the baselines extend very far in terms of time series prediction. So I think long-term time series prediction is really the most urgent question to address. And with our data, we ensured that the test data, for instance, is not seen during training, of course. But with certain long-term time series baselines, we definitely see that the model can't predict as well. And so I think there's just kind of a fundamental limit of something like order 700 or 1,000 time steps, where none of these models are able to generalize well.
And the other question is like, do you know to what extent does XVAL like know the math it's doing? For example, like if you do some sort of like mechanistic approach, like looking at activations, patching them into like some other corrupted run of the model, does it know that it's performing the wrong calculation or not? Because that's something that would provide some sort of validation as to whether it's actually performing the math correctly?
Yeah, it's a super interesting question. We tested on a couple of arithmetic baselines. We tested on multi-digit addition and multiplication, like I mentioned. And we also tested on kind of compositionality. So how many different arithmetic tasks can you kind of chain together? And at least on the chaining tasks, it actually does relatively well. So we come up with a couple of different ways of kind of probing if it actually is capable of predicting multiple tasks on top of each other. But I think in terms of interpretability, which is maybe more what you're asking for, it's something I'm very interested in, but we've only scratched the surface on it.
Well, thank you for the very nice talk. I have a question more on the philosophical side of the talk. So you mentioned, I really enjoy it. You make a connection between the physics and the language, and the physics would be very likely to benefit from the language model. I was thinking about, okay, physics in large is empirical. You collect the data, you find pattern in the data, but also you have some a priori rules like the conservation of energy. There's nobody actually confirm that from experiment. Can you go from but we postulate that from we do experiment, collect data. Especially like when you toss a coin for many enough time, you find okay the possibility of it getting face or bottom is half. Do you think it is possible for language model to postulate the first principle, like the law of large number? If so, how?
I mean, it's a really cool question. Yeah, thank you. I think it kind of gets to, again, like what is our greater goal in creating these foundation models? Are we trying to create automated scientists, or are we creating kind of discrete tools for us as scientists to choose to incorporate into their workflow or not? And depending on who I talk to, some people are really excited about the idea of automated hypotheses, for instance, as a possible outcome. For me, I'm actually less interested in that as an ultimate goal, but please try to build that if you like. And that's kind of, it's a little bit informed by my experience working with this in artistic contexts, where if I train a model to generate an art piece, as an artist, I am not so excited to work with just the pure output. I instead want to really engage with it in a kind of conversation. And so to me, just sort of generating hypothesis is much less exciting than pointing out relationships that exist within one domain and then simply noticing that that relationship doesn't exist in another domain, for instance. So I would want a model that makes me ask more questions as opposed to gives me the answers.
Hello, I have one question regarding the numerical embedding. So do you explicitly also encode the unit? Like, for example, an MEV or an TGV, if you ask them for the math, it can be different, which unit you use.
This is a great question. So we have an extension to Excel that will be on the archive very soon. So I would encourage you to look out for that. But what I've shown today is really just thinking about the magnitude of the number. And so at this point, it's not dealing with overall many different scales or many different units as a possibility, but it's a natural extension.
Okay.
Your output is very nice and a provoking talk. So in some of the AI for math studies, they found also some interesting dependencies on which bases you train on. So, like think like base 2, base 10, and there's also interesting things there. I was curious whether in the Axwell training, did you consider also potential, not just for the math part, but in general, this idea of what's the variation based on what your base hypothesis might be, whatever that means, the base, but not necessarily only in the math sense.
Cool question. Yeah, we only trained on base 10 for now, but I suppose there's questions about the precision of your representation of your number. And so right now, we're just working within kind of a fixed precision. But if we think about sort of moving to arbitrary precision, that might mean different architectural choices. So at this point, not quite, but I agree with you that there are often really key choices about the representation of your data that are worth considering in the overall architecture.
Okay, we have time for one final question.
For time series prediction, what was the size of the training samples for that you used, and same for training and for testing,
Yeah, you mean
the number of samples,
the rollout or?
the number of samples that you used to inform the LLM?
Yeah.
And then, yeah.
Right, so yeah, so we're training these all from scratch, so they're not like pre-trained or fine-tuned rather from pre-trained models. The size of our training corpus is around 1 million examples. And at least in the planetary simulations, they're simulations, so they're cheap to generate. And we provide between 40 or 50 or 60-ish time steps, and we ask it to predict 10 time steps in the future.
Great, let's take Mariel one more time.